talk is on the topic from sand to silicon, the chip design life cycle, the platform perspective. Before I begin, this is a huge topic, right? I mean, I can go for hours and still not probably do justice to this. So I'll try to give you an overview of what I'm going to talk today. This talk is primarily going to be focused on the way we design a chip and how the entire process works, starting from sand and all the way to silicon. And also a sort of an evolution study of how a system has evolved over the last few decades, right? So this is going to be the outline for my talk. I'll cover the golden rule for the electronic industry. What I mean by that, I'll come to that later. The sand to silicon process. Now, in that, I'll focus on the platform perspective, and then the product lifecycle. Now, when I talk about product lifecycle, it has a bunch of stuff in there, right? So it starts with market study. You have to understand what market needs, not just now, maybe 5 years down the line. Then you need to have the projection for the product features, demand, cost, etc. And then you do product planning. How you would like to develop the product, what are the specs and things like that. And then you use that planning to have a product in section as a project. And once you define a project, then you start the design and verification effort for that. After you design and verify, you then go on to doing the system build. So today I'll be focusing on the system build part of it. This is just to give you a very oversimplified view of what product lifecycle means. And after your system is built, you go through debug and qualification and essentially the productization. What you see on the right is all these components are involved in designing a product, silicon platform and whatnot. So it has architecture component, process, design, test and assembly, and then packaging and productization. All these components, they have overlap. What you see in the middle is design. Design kind of has overlap for pretty much all these different verticals, if you will. This is very hardware-centric view, but along with this, you have a software stack definition, which kind of gets defined in parallel to this. And eventually, when a system buildup happens, you need to have software working as expected on all these systems, because I mean, you can have an amazing hardware, but you need to have certain standard and specs for the software defined as well, so that you can make use of those resources to their fullest availability. Before I get into the detail, just for your information, all the material I share here, they're all available in public domain. These are all public knowledge. I'm not sharing anything confidential from Intel. I will be heavily using content that has been published by Intel in the past, but the nature of the data or the methodologies and things like that, they are pretty generic. I mean, the entire industry is doing kind of similar stuff for all these. So yeah, if you want, you can go ahead and search for these articles online, and you will have access to all of that. All right. So what is the golden rule of electronic industry, right? It's Moore's law. Moore's law is what drives the electronic industry. We have seen tremendous growth in the electronic industry over the last 5 decades, starting from 70s and 80s and all the way through what we are seeing right now. In 1965, Gordon Moore made a prediction that the computing would dramatically increase in power and decrease in relative cost at an exponential pace. The more familiar version of it essentially is what you see here, which says it's an observation that the number of transistors in a dense integrated circuit doubles about every 2 years. That's what we are more familiar with, right? So every 2 odd years, that's the cadence, at least that used to be the cadence. We can integrate more and more transistors with smaller and smaller footprint. If you can pack in more transistors, you can pack in more functionality, and you get more and more complex systems at your avail. So that has been the driving factor for all the innovation we have seen in the electronic industry. Of late, there has been concerns There are a lot of notable people who have said, well, Moore's law may be dead. I mean, if you go to the CNET website, actually, NVIDIA CEO said that in CES 2019. There are a bunch of articles. If you go to Nature, they have, this is actually a really interesting article. So what they are saying is, well, you can't push anything beyond what you already have for Moore's law. For all practical purposes, you have to move away from that. There has been this thought that you really cannot push the boundaries of physics anymore, and the pace at which Moore's law has progressed, that's going to come to an end. I'm really happy to see that these predictions are not necessarily true. In fact, Moore's law is well alive, and that's what we are going to actually see through this presentation. Along with these kind of articles, there are a lot of articles which actually talks about the bright future of Moore's law. This is in particular a very good article. You should go and read about that. There have been quite a lot of research going on in terms of developing different forms of transistors, moving away from traditional silicon transistors to nanowire based and a lot of other structures to essentially propel Moore's law beyond maybe next few decades, right? So this is what we have seen over last several years or several decades. So a lot of these PPTs are actually taken from Intel Architecture Day slide. So Moore's law gave us something called exponential entitlement. So if you were in the 80s and 90s, the way process used to scale, you used to be able to get that amount of scaling in terms of beat, power, performance, and whatnot. What this graph shows is the evolution of PC industry, starting from 80s all the way to 2016 and beyond. On x-axis, you have time. Y-axis is the log scale. And we see three different parameters, primarily frequency, performance per watt, and transistor density. In 80s and 90s, the mindset was primarily driven by performance. So that's why we saw something called megahertz era, right? So every few years, you would actually see newer processors coming in the market, which used to run faster. So the primary driving factor was performance. And if you see the rate at which you could scale from the previous generation to the current one, they kind of had a steady and healthy way of becoming better and better. Towards 2000, there was a shift in the mindset. Instead of pushing further and further for frequency, we kind of shifted towards something called multi-core era. Instead of having a bigger and beefier core, one single CPU, we went towards multiple cores for a CPU. There are a lot of reasons behind it. If you keep on pushing for frequency, you hit a limit for power, you hit a limit for your thermal budgeting, for your kind of traces you have on your PCB boards, you hit a bunch of limits from noise and signal integrity and whatnot. So we had a shift from being frequency driven to, you could say, core driven, or the way you integrate the system at a package level. But if you see, at least from a density point of view, we could still maintain a healthy scaling process over process. Of late, 2016 and current, there has been a huge shift in the mindset from being frequency or even multi-core, number of core driven. We have been driven by architecture, the way you architect your systems, the way you integrate. And if you look at here, all these dotted lines, the rate at which the process used to give you the flexibility to double the number of transistors, essentially the transistor density, that has come down. May not be significant, but it's a sizable shift. So, and again, there are a lot of reasons behind it. As and when you shrink the feature size, you are dealing with maybe like molecule level accuracy. So if that is the case, it's extremely hard to control such structures on silicon wafers, right? So your yield gets impacted. So you may not be able to push the density the way you used to push before. So instead of focusing only on the transistor density or even performance per watt and frequency, if you see frequency has kind of been pretty flat. We have seen tremendous growth and innovation in the architecture era, and we'll get a glimpse of that as well. So the intent of showing this slide was to say that the way we used to know a PC has changed completely in last 10, 20, 30 years. This is just a glimpse of what Intel has offered over the years. When I joined Intel, we were working on 90 nanometer process node. We still had like strained silicon structures. Again, I'm not going to get into the detail of what these are, but again, there has been tremendous growth and evolution, if you will, in the way transistors are drawn. So transistors are essentially the building blocks of all these computer chips, right? I mean, these transistors work as switches, which gives you those 0 and 1 in the digital world. So the main focus is from one process node to the other, you make these transistors smaller and smaller so that you could packing more of these. Packing more transistor means more functionality in the same footprint, essentially. Right, so this shows the trajectory from 90 nanometer all the way to 14, and this structure here is one of the latest versions of what Intel transistor looks like. So we had a big change in the way transistor used to be fabricated. They initially started off with planar transistors, and now these are FinFET transistors. So they are very sophisticated, complex structures, and it's extremely hard to control the geometries in the current process node. Here again, this is just to show how different kind of innovative work going on to make transistor even smaller, going away from traditional silicon substrates. So this was shown, I believe, in 2020, and this is taken from Intel Architecture Date, the latest one, right? So this is what we have in 2022 or 2021. It's amazing to see how much we have evolved in just last few years. Again, it shows the same trajectory here, but now Intel actually announced Armstrong era transistor integration. So when we are talking about building these transistors on silicon, we are literally talking about working with 1-2 layers of molecules to control the feature sizes. Again, the intent of this slide is just to show how much transistor and PC manufacturing has evolved over time. These two slides are kind of really dear to me. In 1971, Intel launched its 4004 chip. I believe it was used in a calculator or something like that. It had 2,300 transistors, and you could see only these many pins coming out from the package. In 2020, Intel launched a chip called Tiger Lake, and it had few billion transistors. Right, and of course the footprint, if you see, is comparable, and the number of transistors have gone from thousands to billions. And if you see this, in 1956, IBM launched a less than 4 megabytes of hard disk drive. So this is a hard disk drive, and it's been forklifted onto a plane. And this is 1 terabyte SSD from Micron in 2020, right? So when you look at these pictures, you can easily imagine that how much innovation has gone into designing all these. It doesn't have to be just a PC per se, and how the golden rule, the Moore's law, has actually evolved over time, but also enabled the industry to maintain its growth. Okay, so switching gears a little bit, the topics said sand to silicon, right? So let's see what does that mean. I'll give you a very simplified, actually oversimplified view of what does it take to design a microprocessor, starting from sand. Why sand? This is the silicon industry, right? So silicon is the backbone of these chips. So we need silicon for the primary fabrication process. Now, silicon comes from silicon dioxide, which is found in sand. So that's why we start this at the level of sand. You take sand, and then, of course, you have to extract the silicon from there. It goes through myriad steps of heating it up, melting it, extracting silicon from there, and then purifying it. So from taking amount of raw sand like this, after a bunch of steps, what you end up with is called a monocrystal silicon ingot. It looks something like this. The size or the diameter, if you will, kind of defines the wafer size. So it gets created in this cylindrical shape, and if you see here, the purity is 99 point, like there are like 8 nines after the decimal point, I think. So that has to be the level of purity you are working with for you to be able to fabricate chips. So it's a very complex process. After you get that silicon cylinder structure, you actually then start sawing them with a diamond saw to form one single wafer. So when people talk about, oh, wafer and all that, so this is what it means. So this is a silicon wafer. This silicon wafer actually is the place where you actually fabricate your chips. One wafer can house hundreds of chips, depending, of course, on the size of it. So one wafer has several number of chips, the same design. Then after you get this, you run through multiple electrochemical mechanical steps. I'm not going to get into the details of this. Silicon by itself cannot work as a foundation for designing a chip. So in order to be able to fabricate those transistors, for you to be able to get a logic 0 and logic 1, you need to have a certain number of impurities or different kinds of materials implanted into that pure silicon surface. So that goes on for multiple steps. So there are things like application of photoresist, ion implantation, and whatnot. So these are, again, well controlled and very, very precise steps. After you go through those chemical processes, what now we come to is we print the design onto that silicon wafer. So what do we print? We actually print the design we are designing. So when you define an architecture, then you translate that into design, you draw the layout for all that, and then you have to now print that onto the silicon wafer. So this is similar to what we used to see in the form of old film-based cameras, right? So we used to have a film roll inside the camera. You'd open the shutter, it would get exposed to the light, and whatever you see outside gets printed onto that chemical thin film. Something similar happens. So that photoresist, whatever we saw here for all these steps, they get exposed to a certain design pattern. And again, these are this is very simplified version. Nowadays, the number of so this is called mask. You actually draw these masks to essentially replicate the layout you draw for the design for your chip, and then you shine laser onto that mask. And depending on the structures you have drawn, the certain areas on that silicon wafer either get exposed to that laser light or they don't. Depending on that, it creates a chemical reaction, and at the end of it, you get a transistor structure. In the current generation, there are close to 100, or if not more, masks required for you to be able to fabricate the design on a silicon wafer. And again, these are very intricate processes and requires years of research and maturing this to be able to have some chip which can yield. So again, after going through all these, I'm going to skip some of these structuring steps, which give you transistors. Then you do this metallization. So you can have these transistors, but you have to kind of connect them with wires. So metallization does that. And there are several different layers of that. So after you do all of that, now you have one wafer where you have, let's say, hundreds of individual chips. Each of these chips are your functional microprocessor or SoC or mobile or whatnot, right? Now, before you can actually package them, you need to check whether they actually work at all or not. So they're on arrival. So we do something called wafer sort. So the chip is still on the wafer, and you go and do some sort of a measurement to understand whether that silicon can work or not. So that's called wafer sort. Out of 100 chips on that silicon wafer, maybe let's say 50 only pass those tests. So you have to essentially throw rest of those 50 chips away because they're essentially not going to be working at all. After you do that step, you do something called wafer slicing. So you slice that wafer into individual chips, and those are the ones which would be packaged into a single unit of microprocessor or a silicon chip that you have designed. So then there are a bunch of different software robots which will go and pick the correct chip that's still functioning, that passed the wafer sort test, and pick them up, put it onto a raster. So that's an individual die. So this is what you have defined or created. Let's say it's a Core i5 desktop processor. After you got that functional die, you go through packaging, and then you have that processor, right? So this is what you see in a box when you go to a market and shop for that. And then again, it goes through several other steps. It's called class test. Class test is actually characterizing for performance and power. So you know that functional die works, but you don't know whether it works at a spec frequency or not. So you do that in class testing. These are gigantic systems. If you go into a lab, you'll see these are huge, huge machines where you put hundreds and hundreds of chips together, and it runs some predefined tests to determine whether it's meeting the spec frequency or not. After you do all that, there is an interesting step called binning. Again, not going to get into the detail, just to get an understanding of what it is. Let's say you have 100 chips, 75 of those are running at 3.5 gigahertz, 10 of those are running at 3.5 gigahertz, and let's say 3.6 gigahertz. So you kind of bucket them based on what their frequency specs are or frequency ranges are. And then you can sell them at different price points. So that's called binning. So after you do all of that, it eventually gets packaged into this nice box of retail packaging and then gets sold at the market, okay? So this is what it takes to do silicon chip design, starting from creating a silicon ingot all the way up to creating a package and then selling the chip. Now, what you'll see later in this presentation is these individual steps may be defining the way hardware works or hardware specs are defined, but all these steps have remained the same, but the way they have been purposed over time to enable certain way of integrating or packaging a product has evolved a lot. Now, every processor design or chip design has a workflow to it. This is just an overview. I'll not get into the details of these boxes, but just to let you know that when you talk about a silicon chip, it can mean a lot of different things. Traditionally, we used to call a silicon chip a CPU. It could be a server or a desktop or something like that. So that used to be the primary objective of, let's say, defining a VLSI design process for CPUs. You could have something called ASIC, which are application specific. You could have something called SoC, system on chip. Along with these, you can have FPGAs. Nowadays, we are seeing FPGAs are being used a lot in the form of accelerators. They're being used in conjunction with a regular streamlined server. And then I have some description of that as well. So these are different design paradigms. And most importantly, you still have something called custom. Nowadays, a lot of the design work happens through EDA tools, which are CAD tools, which would actually design some of the architecture-driven or spec-driven designs for you. But if you really want to, for some of the things like, let's say, embedded memories, cache, SRAM, all those structures, they still need manual intervention. The area scaling, the power and performance scaling that you generally achieve on all these process nodes, cache, SRAM, and all these embedded memories, they play a major role enabling that. And there are still designs where people actually hand draw structures to make sure your yield is correct. When you move from one process generation to the next, you are still able to yield at a very high level on your SRAM bit cell. Unless SRAM bit cell works on a given node, no matter how great your architecture is, you are not going to have any product at hand. So in short, whatever your design paradigm may be, it follows a very traditional flow, which you can see on the right. So it's kind of defined in three different parts. One is the front end. Front end basically takes architecture and microarchitecture of a product and translates that into a hardware description language. So this happens at the primary phase of a given product definition and product design. Once that is done, you go on to something called backend. And backend is actually the implementation of that hardware description language that you have written for your architecture. So you take your it's called RTL here. So you take that RTL, take that through autoplace and route kind of steps. You close timing, power, and whatnot, and you convert the design. And when I say convert the design, you actually draw the layout that can be sent to the fab for you to fabricate the chip onto the silicon. And then the last one is called RV, or reliability verification. So you can design a chip, but you have to make sure that it's reliable. It adheres to a certain standard in terms of the number of years it has to work at a certain spec frequency and things like that. So no matter what you are designing, you will see this design methodology in place. Now, I mean, we have always seen this, but off late it has become more and more challenging. There has been always a push for PPA. PPA stands for power, performance, and area. So you need more performance at a less power at a smaller area. So this is really contradicting requirements, right? And that has posed a lot of challenge in terms of designing these systems. And these challenges have actually propelled the way we have moved away from frequency-driven era to what we see nowadays, which is more towards architecture or integration-driven at a system level. I'm gonna skip this. So Saptarshi, maybe we can stop here and see if anybody has any question before we move to the next one.
Sure. So yeah, if anyone has any questions, I mean, today you can maybe just talk. Just unmute yourself and say.
I hope I'm not boring you guys.
No, I think that's not out of the question.
Okay, I mean, if there are no other questions, we can move
So
ahead.
I do have a question.
Can I ask a question?
Yeah, sure, go
Hello,
ahead.
I'm Professor Istiqbal. I try to listen to many of your lectures. I want to know the step where you did that photography and then you were talking about three-dimensional fabrication also. So it's so difficult. I mean, doing all those things, so many layers, how many times you have to expose the film and the details. Those details must be becoming more and more complicated with smaller sizes and almost molecular level. So that is amazing. I
Absolutely.
mean, still how they do with high yield is the
Absolutely.
real question which we do not know how it happens, how we still get working chips with such high density. Yeah, right. That's
Absolutely.
what is amazing.
Absolutely, yeah.
Very interesting.
And yes. And again, I mean, I will not be able to get into it because that itself is a topic on its own, right? And I can go for hours on that.
Yeah, surely.
So,
But we'll get
so
to know multi-layer
yes,
photolithography, etc. Some things we will come to know. Whatever has been
right,
done over the many decades, so we'll know those things.
right. So I think probably what I
And
can
what is
say,
interesting, also the last point you said that now the third trend has started, that architecture, etc. So it shows the
yes,
other things are exhausting, and now we have to do higher level planning, and
correct,
yeah, so that's
correct,
another important thing. So the
correct.
world is
Yeah,
changing very much, even for this course at the undergraduate level. These will have very important inputs for the students.
sure. Yeah, I mean,
Thank
yeah, definitely.
you.
And just to on that note, right?
Yes, please. Yeah,
When we talk about any system, it could be anything, right? I mean, so when we define a parameter, we always take one single value and go with it. But essentially, it's a distribution. It's always a distribution. So when you talk about, let's say, 100 billion transistors on one single chip, you are trying to fabricate really tightly defined dimensions for a transistor. Nowadays, you have, let's say, I mean, we see all these white papers from other fabs like TSMC where they claim they are working on 2 nanometer process nodes, right? 2 nanometer is a mind-boggling dimension. And when you are trying to fabricate a 2 nanometer feature size for 100 billion transistors and associated features on one single chip, not a single feature would be identical to the next one. So if you kind of think of that as a random variable and plot a Gaussian distribution of that, it's extremely hard to ensure that the distribution is not too much so that you don't deviate from your spec. And when you keep on adding more and more metal layers, more and more, as I said, right? I mean, you still have like close to 100, if not more, number of masks for you to be able to fabricate something. Variability has become really bottleneck, right? So variability and associated effects are becoming more and more complex to handle. And that's why if you see the traditional way of fabricating a chip on a 12 or any size wafer, the defect density and the nature of the defect, it has changed a lot. So for you to be able to make money at the market, if you have a wafer where you have 100 single die, if you are able to yield only 5 of them, you're not going to make money, right? So your yield target has to be very close to 100 for you to be able to fabricate functional chips per silicon. So defining one process node is one thing, but it, I think, takes a lot and lots of effort over the years to mature it, which we call process ramp. And if you are able to ramp your process effectively to hit a certain target for your yield, then only you'll be able to have a meaningful design on the chip. So yeah, I mean, it is mind-boggling, and it is quite interesting to see that as well. Okay, let's probably move on. So this is the second part of the talk. So this is where I focus mainly on the platform side of it. We saw what process means, how we actually can fabricate design on a silicon, package it to get a product. now we'll concentrate more on how that product has evolved over time. So the evolution of platform and the corresponding challenges. So you'll see a lot of material here. I won't be able to again cover the details of it. The idea is not to show you what a system is built off of or what different components are. It's just to tell you how it has evolved over time and what are the challenges and what are the places where you could actually see the requirement of innovation. I mean, innovation is required everywhere, and I mean, currently, if you see, each and every component needs innovation, a lot of it, to be able to, propel the growth further. So when you talk about platforms, as I said, going from a single chip era to multi-chip era or multi-core era, we generally talk about three primary kinds of platforms. It could be multi-core, multi-chip, and more recently, heterogeneous platforms. Now, when you move to such chiplet driven or core driven platforms, you have quite a lot of packaging challenges. So you'll see a glimpse of what 3D packaging looks like. To put it bluntly, it's a nightmare, right? So if gone are the days where you used to have, I'm not trivializing the challenges we had before, maybe in 90s and early 2000s, there were still a lot of challenges and people worked really, really hard to overcome those. But the nature of those challenges have evolved over time, and they're very specific the way we see it nowadays. So you have packaging challenges and also interconnect challenges. So when you talk about the integration between hardware and software, you could have 100 cores, and but you need to have an effective way of communicating between those cores in an effective manner. So you need a good interconnect, and your software stack should be able to be ported over from one kind of platform to the other to be able to kind of get most of what you have in the hardware. And that's what the next point says: need for effective software integration. And why we need all that? We need meaningful yield. By yield, what I meant before as well, you fabricate 100 chips, maybe 95 of them are working, so your yield is 95%. You cannot go below a certain percentage, because if you do, you are actually fabricating a lot more material, but you are not making money out of it. Yield and SKU. SKU stands for stock keeping unit. It's related to binning, but let's just skip that part for now. So this slide shows the evolution of platforms in a very simplified manner. The picture you see on the right is a good old days platform we used to see in the form of PCB integration. So we had a CPU, which was a regular, it could be a regular desktop PC chip. And then we had something called a North Bridge and a South Bridge. North Bridge used to work primarily as memory controller hub, and South Bridge used to work primarily as an I/O controller hub. So you have memory DIMMs and whatnot, they would get connected through this North Bridge to the CPU, and you would have South Bridge, which would talk to this PCI Express and other peripheral interfaces. So that's how we saw a platform built on a PCB. From there, we moved into something called multi-core. So it's still a monolithic die, where instead of having one processing core, you had multiple of them. We started with 2 cores, we went into 4 cores, and then we kept adding more and more cores. Not in all of them were of the same capacity, maybe it could be mix and match and whatnot. But the whole idea was, instead of having bigger and bigger core, divide them into multiple number of smaller cores, and then come up with a better architecture so that you can make use of those relatively smaller cores simultaneously to effectively get more benefit out of it. So that was one paradigm shift. And what you see nowadays, more recently, you'll hear all these terms a lot nowadays, like 2.5D, 3D stack, and all that. and they are becoming more and more streamlined. What you see on the right bottom is an Intel Agilex 10 nanometer FPGA platform. I'm kind of really proud of this because I personally worked on it recently, and it was a big challenge for us to be able to design the very first 10 nanometer offering from Intel. And I'll come to the details, a little bit of the details for this. It's a very good example of what 2.5D integration looks like for a system. And what you see on the top right is a Lakefield platform. I keep calling these platforms because they indeed are. Lakefield uses something called Intel Foveros. Intel Foveros is a true 3D packaging solution, and we'll see what that means in a minute. So this, in a nutshell, is kind of the way platforms have evolved over time, the way we know our PC system. What you see on the top is a conventional discrete component integration using PCB. So we didn't have all the time FPGAs integrated along with CPUs. We primarily used to have CPU, maybe some ASIC flash, some DRAM, some analog chips, and we had an actual discrete PCB board. You would actually go and solder these chips on them, have traces run through PCB to connect them, right? What are the issues? A lot. Cost is an issue, size is an issue, the trace length becoming longer and longer. Maybe you have a bigger and a bigger system to be built. If you push for frequency, you have issues for signal integrity at such high frequency. You need different kinds of interconnects. So there are lots and lots of the issues associated with very traditional way of building these systems. So what you see in the bottom are two solutions that has become really, really popular nowadays. These are multi-die integration platforms. What you see on the right is industry standard that has been in place for some time. And what you see on the left is an Intel offering called Intel EMIB. EMIB stands for Embedded Multi-Die Interconnect Bridge. The whole idea is here this picture talks about connecting multiple FPGA die. It could be any kind of silicon die. So you have these 3 individual FPGA die, and you want to connect these through some system. So what you do is, what you see at the bottom is a package substrate. Now you insert an additional package, a silicon substrate, which is called interposer. So this interposer, you can think of this as some sort of a connectivity layer between these different FPGA die. So this interposer layer provides the connection between these different FPGA die. And you have something called through silicon via or TSVs. These TSVs are used also for you to be able to supply power from the package substrate all the way to these FPGA die. There are issues in this. TSV is a very complex process. It has yield implications. The silicon interposer adds a bunch of area and cost because it's silicon. You add more material, it adds to your cost. What Intel has developed is, as I said, EMIB. What EMIB does is it does not require an additional interposer silicon layer for you to be able to connect between multiple die. So it creates a structure like this. Again, it's oversimplified, but the whole idea is you don't need TSVs for you to be able to connect between an FPGA die and an additional die like this over here. And it saves you area, it saves you cost. Since you don't have any requirement for TSVs, it improves your yield significantly and simplifies the overall integration. So where we use this, I mean, this is not necessarily an example for that. What we do is, if you see this Intel Agilex platform here, the central die is an Intel FPGA die. And then along with that, you have a DDR interface, a high bandwidth memory interface. You have some transceivers blocks at this platform level, and you are actually connecting these through that EMIB structure at different dimensions. So at a platform, these individual chiplets, if you will, they can be fabricated using different process nodes, but you could integrate them at this platform level with the help of this EMIB structure. Why do you need to do that? As I said, more and more process advancements we have seen, it has come at a cost of increased variability, defect density, and whatnot. So if you have a pretty big chip, due to the defect density, you would have a lot more defects, and your yield may not be that good. So what you do, you can desegregate your design into multiple chiplets. So you have smaller chips where you could have better yield. And also IPs like transceivers and analog IPs, which are traditionally built on much more matured analog nodes, not necessarily on maybe let's say 7 nanometers, 5 nanometer nodes like that. You can still fabricate those at an older node and still be able to connect them using a structure like this and at a platform level. So you have a kind of a heterogeneous system at a platform level, which kind of serves all the purposes. What we have seen as an evolution, again, from a platform point of view, is you see here, this is an Oak Spring platform. So nowadays you will see a server, this is an Intel Xeon chip coming at this board level, which is connected through Intel Agilex. And each of these can have its own DDR links and other peripheral interconnects. The whole idea is you connect your Xeon chip with an Agilex, and you can use this Agilex chip for acceleration and lots of other stuff. So as a platform, you have quite a different portfolio, if you will, than traditionally having only an FPGA or only a CPU. Now, what you saw here was a 2.5D kind of an integration where you still had these individual die sitting on a package and getting connected through this. So they are sitting side by side, and you're going through this additional package substrate layer to connect them. Moving from 2.5D to 3D, what you see in this picture, this is a true 3D integration where you actually integrate one chip on top of the other one. The example I'm using here is an Intel Ponte Vecchio SoC. Intel Ponte Vecchio has more than 100 billion transistors. It has 47 active tiles. All these tiles are actually chips on their own. So you have 47 different active tiles, and they are actually fabricated using 5 different process nodes. So you could have a compute tile, as you see here, maybe let's say fabricated on 10 nanometer. You could have a base tile fabricated on a different process node. So depending on what kind of IP you have, and then you integrate those in a true 3D stack in a platform like this. So again, I mean, this is an extremely complex process to be able to have such humongous amount of functionality coming from all different kinds of process nodes and pack them into a single package. So that's the evolution we have seen in the packaging industry. Towards the end of this presentation, what I'll do is I'll use the example of something called Sapphire Rapids. This is a latest Intel offering for a GPU structure. Again, it's moving from a single monolithic die to a multi-die design for increased scalability. I'll use this to kind of give you a glimpse of how much a system has evolved from even merely a multi-core or multi-CPU system into something as heterogeneous as it could ever get. So Sapphire Rapids is a multiple tile, single CPU kind of a structure. So if you see, it looks something like this, right? So if you see these tiles, they are replicated like 4 times here. You have different cache blocks, you have PCI blocks, you have accelerators, bunch of I/O interfaces and memory interfaces. So in this current generation of integration, what you can actually do is, instead of building this humongous die on one single wafer, you can actually fabricate these separately on maybe separate process node, depending on which one is more tuned towards a certain kind of an architecture, and then integrate them back using this 3D Stack Foveros platform, and get this system up and running, right? So I'm gonna skip this. So if you see this structure here, instead of having a monolithic, simplistic CPU where you may have some sort of an ALU, a memory controller, a bunch of cache, and I/O, you have the primary differentiation from a previous set of platforms to the current one is the integration of the heterogeneous platform. So one example of that is a true CPU, which is let's say a compute, and accelerator blocks. Now, why we need these accelerators, right? In a traditional system where, let's say, you have these 4 cores and you are running some sort of a process which requires all these 4 cores to be utilized, what can happen is you can have some sort of a common mode tasks which are being worked on by all these 4 cores. What you can do is, if you have avenues, you can offload those common tasks onto something, maybe let's say one additional core, so that these individual cores can run more important processes, right? Which are maybe waiting in the queue to be scheduled. So that's exactly what these accelerators do. So you still have these 4 cores, and along with that, you have these 2 accelerators. Now, all these cores have access to these accelerators using some sort of an interconnect protocol. Now, the difference you see between this picture and this picture is those common mode tasks have been offloaded into these accelerators. There are still some going on here, here, and here. So what happened from this picture to this is here, all these cores are fully utilized. I mean, if you have, let's say, number of processes waiting in the queue to be scheduled by the operating system, you really can't do anything because that entire resource is utilized. But if you're able to offload a bunch of that onto the accelerators, the additional workload capacity increases humongously, right? So you can then spend that resource onto completing some other task. It can give you parallelism, more throughput, and whatnot. I'm probably running out of time. I will probably breeze through this. So this shows again the heterogeneous nature of the way the IOs work here as well. For those of you who have seen computer organization, you can have a multi-core, multi-processor system where you have quite a lot of memory shared among those. The biggest bottleneck or biggest headache, I would say in a very simplistic term, is the coherency. You really need to have coherent protocols defined for you to be able to utilize that massive amount of capacity and resource you have. You can keep on packing more and more cores, more and more cache, but unless you ensure that the coherency is maintained, there is no point of having so much of resources. So IO structure has also again evolved over time. You can search for CXL online. I mean, CXL is a recent protocol. Is an interface for primarily heterogeneous system. The interconnect definition is pretty new. That's why you see a 1.1 spec definition here. Intel worked with a lot of other vendors, close to 20 plus vendors in the industry, to come up with this industry-defined and supported now IO protocol, which ensures coherency in such heterogeneous system. Traditionally, we used to have maybe a DDR or a PCI kind of an interface, but now with so much of different tile integration, you would see these very complex heterogeneous protocols coming in. And the speeds we are talking about have evolved quite a lot. I mean, when I started my career, we were still working on PCI Gen 1, Gen 2. Now we are talking about speeds for PCI Gen 5, which has increased quite a lot. So just on this platform itself, you can see there are a bunch of different kinds of I/O protocols that are being worked on, and they're not platform agnostic, but they can be ported over from one system to the other. So that's what kind of supports your heterogeneous nature of these platforms. Same is true for here. What I was talking about, I mean, if you see the LLC capacity is more than 100 MB. That's humongous amount of cache to work with, right? I mean, that's great, but you have to make sure that you are able to maintain that coherency across all those processor cores. Similarly, this is something that you will see more and more in the industry, which is called HBM or high bandwidth memory tiles. HBM has been there for some time in the industry. The whole idea was to kind of get the benefits of be it HBM or Intel Optane memory, things like that, to get the benefit of those SSD, very fast, low latency kind of structure and very high capacity as well. Again, before either you would have a discrete memory card or a discrete memory chip on the PCB, or completely embedded memories which are of very small capacity. Now what you have is these HBM tiles connected through EMIB kind of structure to your actual compute tile to be able to kind of get the benefit of both the worlds. All right, so I mean, in conclusion, I think what you saw was Moore's law is still alive, it's very much alive, and chip design mindset has changed from being frequency driven to code driven to data driven. So when I said architecture driven, architecture is actually catering, or at least trying to cater towards this huge explosion of the data that we are consuming and trying to analyze every day nowadays. So current generation processors, current generation platforms are truly data-driven systems. Chip design lifecycle we saw has lots of interesting challenges, and we really need lots and lots of innovation in each of those areas. And keep in mind one thing before I conclude my talk, that each and every one of these design, be it design, verification, debug, integration, system development, system stack, software stack integration, all these components are equally and extremely important. Every bit of these aspects need to work flawlessly for you to be able to create such a high-performing, well-maintained and well-validated system at the end, right? Thank you. I think that's all I had. Questions?
Thanks, Amit. Yeah, so any questions? So feel free to speak today. No, I mean, for today, no need to write on the chat or raise hand.
Hello, am I audible?
Yes.
Yes.
I actually wanted to ask a few questions. First of all, I would like to ask that in the previous slides, you mentioned there were three phases of the development, right? In which the latest one is the architecture one.
Mm-hmm.
So based on that architecture, wouldn't that change the software development cycles as well?
Yes, definitely, right? So the way you integrate your software stack onto these have definitely evolved over time. So the way you deploy a software solution onto maybe a single processor system to something that we saw currently, let's say a 3D package system, will change. However, depending on the level of abstraction of these hardware resources that get exposed to your software interface, that's probably what is going to define how much it will change, right? So when you build a system and then you, let's say, design a software stack around it, so there are different level of abstractions of that hardware that gets exposed at a different layer for your software. So depending on how much they get exposed, it will change. For some of the hardware solutions or benefits that you get by doing a 3D stacking may not necessarily require to be exposed, right? I mean, from a software utilization point of view of the resources, for certain aspects, you may not necessarily need to kind of see the, let's say, the different stacking of the memory that you have access to, right? So it may come from any different compute tile in that entire package. If that abstraction is not required, maybe that specific aspect of software doesn't get impacted. But yeah, in general, it will.
Okay, yeah, got it. And the other is what can we expect in the future based on that on chip paradigm? Like currently the nanometer size and the nanometer size is decreasing and the count of transistors is increasing, right?
Right.
So what can we expect in the upcoming future, if you can?
Well, what I can say is future is amazing. So when you see these data coming out, I mean, these have been in development for probably a decade already. So I think the next big thing in the VLSI industry is EUV. So the way we shine laser on the silicon substrates, the way we draw this, it depends on the wavelength of the laser or the light source that we use. Now, at such small feature size, it becomes extremely hard to kind of control all that. I probably have a slide, and again, let me check if I have a slide. Yeah, so if you see this, I mean, in picture, it looks pretty good, right? So you want to draw something like this, it comes out like this, but essentially nowadays what's happening is the complexities of creating these masks have gone, I mean, over the roof. More and more complexities are going to come in future. From going from traditional lithography, industry has been trying to move to extreme UV, extreme ultraviolet for a long time. It takes a lot of R&D cost. It takes lots and lots of sophisticated machines to be up and running and predictably printing transistors for you, so that again your yield is pretty high. So yeah, I mean, future is pretty exciting. You'll see more and more releases coming from not just Intel, from a lot of other fab vendors in terms of what they're trying to achieve. I mean, as I said, I mean, TSMC is also working on very small size feature sizes. So yeah, it will be exciting to see what other people can achieve in near future.
Okay, great. Thank you so much.
Sure. I can't hear you.
Hello.
Okay. Yeah. Now I
Sorry,
can
I
hear
was
you.
muted. Yeah. Oh, okay. Okay. So thanks for some question answers. So yeah, one quick question from my side.
Mm-hmm.
Not sure if it is how relevant it is, but still. So nowadays we hear a lot about these GPUs for running neural models and so on. Like I personally have to buy GPUs which cost a huge amount and all. So I was just wondering, like, why does it need to be a separate GPU? I mean, why? I mean, like even in future, like is the possibility that we will have something inbuilt in a processor itself, at least more cores?
So if you go and see how Ponte Vecchio and the platform I was also talking about, right? So they have been developed using GPU mindset, right? So that platform as a whole is GPU driven. Now you could have a discrete GPU, or you could try to have an integrated GPU per se, right? Even you can have a compute unit which can kind of cater as a GPU as well. So I think there are several reasons for it. I mean, if you want to kind of right. So if you want to optimize for a general purpose CPU compared to a GPU kind of a solution, you need to understand how much scalability you have. So If you want to have everything inside a single system and still have the functionality of both, maybe your feature size or the feature space may not be as good as you might have if you had those as two discrete systems. Currently, if you see these accelerator-driven platforms where you can actually offload a bunch of, it's a bit for AI-driven workloads. If you ask somebody at Amazon before Christmas, they run all these workloads to see what customers are buying the day before Christmas and what they're buying the day after. So those are actually being done using these heterogeneous systems because it's much more efficient, because you can reprogram them or purpose program them as you want it. So today you might be running one particular AI algorithm, tomorrow maybe something else. If you see the way these CPU servers are also built, and if you try to do something like that using a CPU server, you may need to do some sort of hardening of the hardware towards catering that particular kind of a workload. So you can say, I don't want to cater to 10 different workloads. I'm going to build my own system. It's going to cater to this very specific workload. You can do that. But again, it's not general purpose anymore. So instead, you go to this heterogeneous system where you can change or modify your algorithm from one day to the other and kind of still get the benefit of the compute resources you have.
Yes. Okay, at least good to know that people are thinking in those lines, but I understand that there are much more like factors which need to be taken into account, what we understand.
Yeah.
Great, thanks for the talk.
Sure.
Yeah. So if there are no more questions, we can close the session. Anyone?
All right.
Okay. Thanks a lot again. Yeah, it's quite late at night. So yeah, good night.
All right. Have a good day.
Thanks again.
All right.
And thanks everyone for attending. Thanks.